Good morning, everyone, for another half an hour. Alrighty, couple announcements before we get started. Nothing particularly new except for one of them. So test number 2 should have all been sent back. Solutions have been posted. If you have any questions about it, as some of you already haven't been shy of doing, please do let me know. Test number 3 is upcoming. It will cover up to the end of chapter 2. That might be your opinion. Up to the end of chapter 2. Some people have been asking. So when I say up to the end of chapter 2, that's just basically how I will phrase it going forward. I think I mentioned this before, but just in case I didn't, we're not directly testing older material, so we're not going to be testing directly the stuff from chapter 1. So really, test 2 is on chapter 2 stuff. That being said, math is cumulative, so obviously you'll see the earlier material showing up constantly throughout the course, but in terms of direct questions, they'll come from chapter 2. All right, and lastly, I'm not going to talk much about it, but I know some people have been stressed out a little bit, so I just wanted to give you all the information I have in regards to possible job action. Again, a lot of you in first year, so you wouldn't have been around last year where they talk and talk and talk, and then amazingly, things may or may not happen. So, but for planning purposes, just to let you know, the test, any possible job action will not affect test number 3 and will not affect your midterm next week. So the midterm is happening no matter what goes on. So make sure you're planning accordingly. The midterm next week, Wednesday evening, is happening, period. So don't get confused with all the other stuff you might be seeing going on. Obviously, test 3 finishes before any possibility of anything. But for your own planning purposes, the midterm is happening regardless. I just said test 3. We don't have the midterm material. Yes, the midterm material is we're still finalizing. I expect something to get posted to Learn today, is my expectations about the cutoff for the material for the midterm, but there's still a little bit of debate about it. My best guess is 3.1, but any confirmation of that will happen later on today. All right. Yes, this is being recorded. I've only messed that up once, and that was in my other class. So. All right. If anyone has any other questions, feel free to keep firing them off. No, so I'll have more details that I'll be sending out later this week in regards to the midterm, but it won't be in your lab section because our TAs invigilate multiple, have different labs, so they can't do them all at the same time when it comes to the midterm. So there will be different invigilators than you're probably used to. At least the majority of people have different invigilators. Some of the details are still being finalized, worked out, but the process will be the same, as in you will go on WebEx, etc., but you'll go to the A01 to A04 page, not the tutorial page. So that being said, log into WebEx, getting it from CrowdMark, all that kind of stuff will be exactly the same, but you'll log in through the A01 to A04. But I'll be sending out an email to the entire course later on this week with a lot more details about that. Although I do think I put it in the course outline anyway. Any other questions? All right. So we're moving on. We're in chapter 3. Chapter 3 is all about vectors, and I can stop being coy in terms of things that I'm saying that I really want to say vectors. So what is a vector? And I know there's like multiple different answers to this, so fire them off. It doesn't have to be my answer. Right. So a vector is an object that has some kind of direction and magnitude. That's effectively it right there. Right? It has a length, it has a direction. That is essentially what we're talking about when we're talking about vectors. Right? Those are the only two things we really care about when it comes to vectors. What is its length? What is its direction? Except there's one vector that is an exception because every rule has to apparently have exceptions. Yeah, the zero vector is the exception to this. What is the exception when it comes to the zero vector? Yeah, it doesn't have a specifically defined direction. Now, some people like to think of it as having no direction. Some people like to think of it as every direction. I kind of like the second one more than the first one. But what everyone can agree on is there's no specific direction of the unit vector, whether you want to think of it as none, whether you want to think of it as every vector, however you want to think of it is perfectly fine. But the point is that it doesn't have a specific direction. But it does have a length. The length, of course, is just 0. All right, so we're going to start by dealing with some of these things, what it means to be working with vectors geometrically. We'll get to the algebra shortly enough, but we really want to focus on the geometry because in this class, in this chapter, and even beyond this chapter, our focus is going to be on two things. Number one, what our vectors, how do we compute with them? How do we use them? When we want to use them, we usually want to use the geometry. When we want to compute them, because it's easier, we want to use the algebra. So we want to think of this in both different ways. So geometrically speaking, when we multiply a vector by a constant, what does that do to the vector? Let's be more specific about how much longer. Yeah, so it makes it longer by a factor of k. Careful, when you say longer by k, that kind of implies you're adding k. So it's k times as long. Right. So, and has the same direction. All right, so if this is our vector v, then this is approximately our vector 2v. Twice as long, same direction. Does the same direction thing work for all values of k? No, it works for half of them. What happens in the other half? Right. If it's negative, we're in the opposite direction. There's negative 2v right there. So if k is negative, then that means we are k times as long. So for example, this one, we're negative 2 times as long in the opposite direction. Wait, that didn't make any sense. So if k is less than 0, then what's k times v? How many times as long? Nope. Absolute value of k times as long. You can't be negative 2 times as long. Length is a positive quantity. You can't be negative 2 times as long. So if we're multiplying by a negative, the length is that absolute value. So the absolute value of k times as long. All right. But, I mean, the negatives aside, if we're multiplying by a constant, at least in absolute value, it's that times as long in either the same or the opposite direction, depending on the whether it's positive or negative. I'll get to the notation stuff. In a minute. If we add two vectors together, what does that do geometrically? What does it do geometrically to add u and v together? I mean, yes, but what is the resultant vector? Yeah, so we would take a copy of v and shift it to the end of u. So the first thing to know, again, let's go back to my first question. What is a vector? What is a vector? Right. It's a quantity with the magnitude and the direction, which means all we care about is the magnitude, the length, and the direction. We don't really care about where it starts and where it stops. So I can take a copy of v and just shift it over here, and as long as I'm going in the same with the same length and direction, we'll consider those to be the same vector. All right, and then somebody said tip to tail. That's what we've done here. And what is a plus v? Or u plus v. Don't know where a came from. U plus v. Yeah, we take this, what we call a diagonal, although we have to be a bit more specific about that. But that's going to be u plus v. In other words, we're going to stick v at the end of u, and then we'll go from the start of u to the end of v. And that's going to be u plus v. All right. What about if I did v plus u? Would that be the same thing? Yeah. Yeah, because if we take a copy of u, we'd stick it there. What shape are we creating? Yeah, we're making ourselves a little parallelogram where u plus v and v plus u are the same thing. We're just taking a different path to the opposite corner. So if we wanted to do u plus v geometrically, we stick v at the end of u and go from the beginning to the end. Right. Any questions about, again, algebraically speaking, geometrically speaking, how we add vectors together? All right, what if we wanted to subtract them? What if we wanted to do u minus v? There's a couple things we could do here. We have a few options. Yeah. So the first one somebody mentioned was tail to tip. We can definitely do that. It's actually this vector right here. That's u minus v. Personally, my problem with that, I mean, it's technically not a problem, but my problem with that personally is I never remember which way to go. But if you can remember, we're subtracting v, we're subtracting v, so we'll start from the end of v and going to the end of u. If you can remember that, then this works just fine. Personally, because I can never remember that, I like to think of it as somebody else had mentioned. And if we're going u minus v, we're going to add the negative of v. So option number 2 is to take v, and how do we get negative v? Opposite direction, what about the length? Same length, yeah. Negative v is the same length, opposite direction, and then we can stick it at the end of u. And we get u plus negative v, or just u minus v. So if we actually look, and I know my picture is not perfect because I'm freehanding this thing, but if we look at u minus v there and u minus v here, we actually do get the same vector. Yes, it's not in the exact same place, but it has the same length and the same direction, which is what we care about. All right, so any questions about how we can geometrically multiply by a scalar, add vectors, or subtract vectors? All right. So I'll give you a couple minutes and see if you can figure out how to draw these three vectors and what these numbers all mean. So I'll give you a couple minutes to draw these things. Will we learn polar coordinates in this course? Kind of. We won't call them polar coordinates, but we will work with trig and some angle stuff, which effectively is very similar to polar coordinates. So we will see some of the building blocks, but we won't be using them in the same way you would use polar coordinates, let's say in a calculus or a physics class. All right, so hopefully you've had a chance to even think about it, maybe get the first two. The third one might be a little bit more challenging depending on your artistic skill, of which I have very little. So when we say the vector 1, 2, what do we really mean by that? What do we mean by the vector 1, 2? Yeah, so when we say 1, 2, we mean the vector that goes 1 unit in the positive x direction and 2 units on the positive y direction. Now, for reasons that of just convenience, we like to have our vector starting at the origin. That being said, as we've already talked about, it doesn't actually matter where the vector is. What matters is its length and its direction. So, but if we started at 0, 0, we're going to go 1 unit in the positive x direction, 1, 2 units in the positive y direction to get where it ends. And then we get our vector that way. So that's how we can draw a vector 1, 2. That being said, if we just decided to start over here at the point 3, 1, then we would still go 1 unit in the positive x direction, 1, 2 units in the positive y direction, and we could still get the exact same vector over here. So it doesn't actually matter where you start and where you stop. Although for convenience, as somebody mentioned, we do like to go from the origin to the point 1, 2. All right, so any questions about how we can graph the vector 1, 2? All right, so note, if we start at the origin, so this is just what I said, but I want to write it down for reasons. If we start at the origin, which sometimes we'll just use the letter O, then vector 1, 2 ends at the point 1, 2. And it's for reasons like this that we almost don't care about the difference between points and vectors. Right? You'll notice we're using the exact same notation we would normally use for a point. And we're going to use that same thing because if we start at the origin, points and vectors end up at the exact same place. All right. So any questions about how we drew this, or kind of this idea that, if we start at the origin, the vector and the point ends at the same place? We'll talk more about the connection between points and vectors a little bit later. All right, -3, 1. How do we draw -3, 1? Three units left and 1 unit up. 1 unit up. Bang, we get our final. We get that right there. And we'll talk about a lot of things. Obviously, we haven't found the lengths of these vectors yet, or how to find the lengths. We'll get to that today. We'll talk about the angles between vectors. These are all things that we're going to be seeing over the next class or two in terms of connections between vectors. All right, any questions about how to draw the vectors 1, 2 and the vectors -3, 1? All right, so we say the vectors 1, 2, and -3, 1, just as a notational thing, we say they are in, for now, we'll just call it the set R2. R2. So in terms of this notation, what does this R thingy stand for? Right, the real numbers. That should be a notation you're familiar with. It just stands for the real numbers. This superscript of a 2, what is that representing? Yeah, that's telling us the dimension. So we're in 2 dimensions. These points are in 2 dimensions. That should have been negative, but the point still stands. That we're using 2 variables. For, in this case, the x and the y. We have 2 dimensions, 2 numbers in our vectors, R2. In this class, all of our vectors are going to be real. We're not talking about complex numbers. If you're familiar with complex numbers, you can do vectors with complex numbers, but we just aren't in this course. Is R2 synonymous with 2 space? The answer to that is yes, although we're not going to be talking about things like vector spaces, subspaces in this class. But yes, it would be in kind of a little bit more advanced than exactly where we are here. So if you want to call it 2 space, that's absolutely fine. But that is something with a very specific definition that for those people taking linear algebra 2, you would talk about that more. All right, so what do we do about 1, 2, 3? The point, or the vector 1, 2, and 3. What's the difference there? Yeah, so we're going to do 3 dimensions, and here is where my lack of artistic skill will be on full display. So, as a big concept idea, some people who've taken physics, you might be familiar with the right-hand rule, where one's the x, y, and then the z is pointing up. If you're familiar with that, we are following the right-hand rule. If you're less familiar with that, then we're going to say x is in this direction, y is in that direction, and z is in this direction. But x, y, and z have to be in very specific places. You couldn't mix up x and y, or else it messes up some of the concepts we're going to be seeing. So people familiar with the right-hand rule, we're following the right-hand rule. For people unfamiliar with that, feel free to look it up. But in this class, we'll just make sure we're using x, y, and z where they are. All right, So anyway, 1, 2, 3. What does that mean in this three-dimensional world? Yeah. 1 unit along the x-axis, 2 units along the y-axis, and 3 units going up the z-axis. So in the end, we start off at the origin, and we're going off in that direction. So again, this isn't perfect. Depending on your artistic skills, it might look a little bit better than mine, but the idea is the same as what we did before. 1 unit along the x, 2 units along the y, 3 units along the z, going from where we start to where we finish. And no, we're not going to be testing your artistic skills with vectors, but this is more just for your own understanding, visualization, either in your head or on the paper, of what's going on. All right. Any questions? Yeah, I went 1 unit in the x direction, 2 units in the y direction, 1, 2, 3 units up. And then went from the start to the end. And then you erase all your little markings, and out pops our answers. For the third, yeah, so we would use x is always going kind of down to the left, or it looks like on our paper, but obviously, you know, if you had, for whatever reason, my camera's not showing to me, but you would have 1, 2, and 3 directions here. So there's your x, there's your y, there's your z, in general, right there. Do things better with visual aids than I can certainly draw. Again, but the purpose of the drawings is more for you to get an idea of what's going on, not necessarily that we're going to be testing your ability to draw these things perfectly. Just a general idea is what we're looking for. All right, if you have any more questions about that, feel free to keep firing them off. Otherwise, now that we hopefully have a little bit of a piece of the geometry, we can start dealing with things from algebra. So given 2 vectors in R2, see if you can get these questions right here. Like the points on the axis, I'm not quite sure how to parse that into a question. Unless there's more of it before. Oh, do you have to label the axes? Yeah, it's always a good idea to label your axes. All right, so from a notational point of view, our textbook doesn't use the arrows, but most textbooks use a bold letter. But that is incredibly difficult to draw, either for students on a piece of paper or me on my OneNote, to actually draw this bold-face V, which is how most textbooks like to denote vectors. So I will be sticking with using an arrow over top of the V. I do know that a lot of people have seen other ways of writing vectors, maybe with a little bar over top or an arrow over top. There might even be a couple equivalent other ways of denoting vectors. But what's important is that you are using some kind of vector notation. So whether you use the little bar here, that's fine if that's what you've seen before or comfortable with, no problem. An arrow is what I'm assuming most people will use. That's great. But some kind of vector notation is needed to distinguish between, for example, if I write KV, it's, you know, if I just write KV like this, how do we know which is the scalar and which is the vector, right? You need to put the arrow over top of what you're calling a vector. So some kind of vector notation is needed, but I do know some people have used other types of vector notation. That's fine, but some vector notation is required. All right, anyway, notational rant. feel free to give these questions here a try. A superscript of a vector, like v with a little arrow here. As in you said, let v be a vector. Oh, really? That's a new one for me. I mean, if you really want to, I'm okay with that. But why write out the word vector when a little arrow gets the job done? But I have no objections. From a teaching educational point of view, I can see the reason why writing v to the power of vector might make sense, but no. All right, so algebraically speaking, how do we add these two vectors together? What do we get? Did I write these down right? Yes, I did. Yeah, so honestly, adding together vectors would be only limited by your ability to add together numbers. You add the first components together, you add the second components together, out pops our final answer. In this case, -1/6. So from a geometric point of view, I know the definition of how to add things together might be a little confusing if you've never seen it before. But the point is that doing it algebraically is a relatively simple calculation, but it has some nice geometric properties that we'll see along the way. And yeah, if there were three, it would be very similar. We'll see an example of that as well. What do we get if we subtract these vectors? Almost. I'll give you the 3. Boom. Yeah, so again, subtracting vectors, we subtract the components. Again, just be careful when you're subtracting a negative. Sometimes that can make things go weird. How about multiplying by a scalar? Right, just multiply both entries by -3. The negative here, if we think about why this is the same thing as the geometry, the negative would make the x the opposite of what it was, the y the opposite of what it was, meaning that we would go in the opposite direction. In terms of the length, it would make the x 3 times as long, the y 3 times as long, and we can get that as well. Can you write it as 6i minus 12j? Sure, if you would like. I haven't talked about that yet, but we will talk about those elementary vectors, ij, ijk. We will get to there, so if you're familiar with that, feel free to go with it. If you're not, you will be by the end of this week for sure. All right, any questions algebraically how we got 6, -12? All right, and this linear combination of u and v, where we multiply them by numbers and add or subtract them. So this is 2 times 1, 2. minus 3 times negative 2, 4. And what do we get as an answer for that? So multiplying by 2, we get 2, 4, minus multiplying by 3, negative 6, 12. And then 2 minus negative 6 is 8. 4 minus 12 is negative 8. We get 8, negative 8. Okay. So, any questions algebraically about how to add, subtract, multiply vectors by scalars, or a combination of all three of them? I guess 2 of them, for the last one. All right. So somebody asked if we did to 3 vectors, would things change? So again, a little quick example. Give these ones a try. But the quick answer is the ideas don't really change no matter how many components we have. Oh, yeah. I'll leave it up to you. I know the question said geometrically. I'll leave it up to you to see geometrically. I'm going to let you, just in interest of time, on your own to try drawing these things geometrically and then just see how that what we get algebraically does seem to match what happens geometrically. So for both the last one and this one, I will leave it, I'll leave the geometry thing to you, just like we did before. Yeah, I made the same mistake on yesterday with my other class. Can we let all n vectors originate at the origin? I mean, the rules say you can, but in practicality, we want sometimes the flexibility to use both. So for example, we'll talk about getting vectors from points and looking at things from points in 2 or 3 space. And so we want to be comfortable enough to be able to work with that as well. But from a strictly adding things together point of view, if you want to add them geometrically, you can make them all work from the origin just to get used to the ideas, which is what I really want you to do. Yeah, I'm just doing adding algebraically. I want you guys to try doing it geometrically on your own. The purpose of that is to just see that what we do algebraically matches what we expect geometrically. You can take my word for it. I mean, it does. So feel free to take my word for it if you just don't want to. But if you want to see that, feel free to add them geometrically like we did in our first examples, that first page, and see that what's going on here actually matches. Or you can just take my word for it. That works too. All right, so again, if we have 3 components, so we have vectors in R3 now. So what's our first component of our answer going to be? Yeah. So our first component is going to be 1. Oops. 1 plus 2 times 2. What's 1 plus 2 times 2? Bang, that's right, 5. For our second component, 1 plus 2 times negative 1, which is negative 1. And 2 plus 2 times 0 is just 2. How would you graph a negative 1 in 3 dimensions? You would just go, instead of moving 1 unit along the y-axis, you'd just be moving 1 unit in the negative direction of the y-axis, if you were doing it in 3 dimensions. So if you go back to our 1, 2, 3 example, if let's say this was 1, negative 2, we go 1 unit in the x direction, and then 2 units in the negative y direction before going up. If we had and similar for any negative of those quantities. Regardless of the direction you're going in, the negative would just make it go in the opposite. All right, so u plus 2v would be 5, negative 1, 2. As for the other one, 3 times 2, negative 1, 0, minus 2 times 1, 1, 2. And I lost some arrows here. What did we get for an answer to that one? Some people are paying attention. Yeah. So again, in terms of calculations, it's really just a whole bunch of adding together numbers, which is as easy or as difficult as you find adding or subtracting numbers. All right. So any questions about how to add, subtract, multiply vectors by scalars in R2 or R3? Yeah, V was first. I tried to fake some people out. Or I just copied and pasted on my little spreadsheet. One or the other. I'll let you figure it out. All right. So we're doing this in R2, we're doing this in R3, but in actuality, there's no reason other than geometric reasons. There's no algebraic reason why we have to stop at 3 components. We could do 4, we could do 5, we could do 20. Might take a while, but we could do 20. And the idea is, algebraically speaking, nothing changes in terms of the ideas. So again, give the same 2 computations a try with these vectors in R5. Your guess is as good as mine as to what this would look like out geometrically. Yeah, so the idea is this is an algebraic statement. So I know vectors are very geometric, and in R2 and R3, even in R1, if you just think of a number line, you could talk about stuff being done geometrically. Once you get past 3 dimensions, I know my brain breaks when I start to think about what these might look like geometrically beyond 3 dimensions. But there's a lot of stuff we'll get and uses we get from algebra with these that we will see, even if the geometry doesn't really help us very much. The algebra certainly will. But the point being is that it really doesn't change how we compute them algebraically. Just more things to make arithmetic mistakes on, that's all. -5, -4, 12 minus -2. Oh no! Bummer. What are you talking about? I don't know what you mean. Looks 3 to me. I'm not sure where you're seeing this -3. Oh darn, I'm reporting this. Busted. Yeah, sorry, when I did this originally, I put -3, just a copying mistake. So I fixed it up, all the changes I made there. So if we use 3, then 3 plus 10 is 13, not 7, which I had before. And same thing with the other one. Try and hide your mistakes, you don't learn from them. All right. So any questions about how to add these things, subtract these things, multiply? Honestly, it doesn't even need to be R2 and R3. We can do it in Rn, any. In this case here, R5. The algebra just does what the algebra does. Righty. So that's how we can work with the components. But let's kind of talk about points here as well. So here, instead of talking about vectors, we're talking about 3 points. So what I want you to do with this example is, given these 3 points, find the vector. When I write this little AB with an arrow, what are we talking about? Yeah, the vector starting at A, finishing at B. So given these 3 points, find the vectors AB and the vectors BC and verify that AB plus BC is actually equal to AC. Give that a try. Do we have to have the same dimensions to add them? Yes. Yeah, so we're not going to take a vector in R2 and add it to a vector in R3. That wouldn't make any sense. Can you never bring R4 plus calcs in the test? I don't see why not. I mean, kind of depends on the usefulness of it. I mean, as we're going to see as time goes on, especially once we get through the next couple sections, I mean, just working with things in R4 and R5 actually makes sense given the context we're going to be using them for. So I don't see why we wouldn't do it. Should you forget matrices? I wouldn't. All right, so how do we find AB? So given 2 points. So here's kind of the difference. If you ever see this written by itself, we're talking about a vector. If you're seeing a letter, specifically a capital letter, in front of these numbers, we're talking about a point. So if you're ever curious as to whether we're using a point or whether you're using a vector, points come with letters in front of it. Point A, point B, point C come with letters in front of it. But from a vector point of view, how do we find the vector? from A to B? Effectively, yes. Yeah. Effectively, yes. That's going to be 2, -1, 0, minus 1, 2, 3. In other words, it's 1, -3, -3. So, yeah. I know subtract, not add. Why do we subtract? Great question. Anyone got an answer for that? Why would we subtract? Wonderful question. I'm actually going to do this in 2 dimensions. So I'm just going to pretend like just for um, easy visualization, I'm going to do it in 2 space, but the ideas work in higher ones. If we go 1, 2, there's A. And if we go 2, -1, there's B. How many? We're going from A to B, if we're going from point A to point B, how many units do we have to travel in the X direction? If I'm starting at A and finishing at to B, well, I've already gone, A itself is already 1 unit in the X direction. We have to move 1 more unit in the X direction. In other words, the X's is 2 minus 1. In the same way, if I gave you a number line and said, here's 0, said, I'm at 5, I want to get to 7, how many units would you travel to go from 5 to 7? We'd go 2. Yes, exactly. So AB is starting at A, finishing at B. And that's why we're subtracting. Right. Any other questions about how we get the vector from A to B? All right, BC. Didn't get it? So if you're on a number line and you're at 5 and you want to go to 13, how many units do you have to travel? That's why you subtract. 13 minus 5. And there's nothing special about, I did it in 2 dimensions so I could draw it more nicely. But the ideas still work in 3 dimensions. And if you want to play around in higher dimensions, the algebraic ideas would work there. Kind of. Yeah, we can, it's, the X is the run, the Y is the rise. So there's connections with slope. So you're doing the same kind of calculations you would for slope, but for a different reason. All right, so for BC, what do we get for BC? One, -3, 1. Beautiful. And what would AC be? That'd be 3, 4, 1, minus 1, 2, 3. And so we get 2, -6, 4. No, not 4. Nonsense is that? All right. So here's AC, here's AB, and here's BC. And what should hopefully, if you look at these 3 vectors, what's the connection between them? Yeah, AC appears to be. Now, somebody just asked, and it's a wonderful question. Is that a weird coincidence, or is that something we should expect? Just because it worked in this one example doesn't mean that it always works. So can someone give a geometric reason why this makes sense? Why does AC equal to AB plus BC make sense? Yeah, it's exactly how we add together vectors geometrically. So if this is, I'm not saying this is what these vectors look like, but if this is A, this is B, and this is C over here, here we have the vector AB, here we have the vector BC, and there we have the vector AC, which is exactly how we add vectors geometrically. So the fact that AC is AB plus BC is exactly what we should expect every single time. All right, any questions about adding vectors, subtracting vectors, or kind of given 2 points, finding the vectors from one to the other? All right, so in my notes here, this is the same thing we talked about before. Because if we start at the origin, the endpoint and the vector are the same, that we don't actually distinguish most of the time between a point and a vector, because any vector can be thought as the vector starting at the origin and finishing at the point. So that's what we talked about back when we were drawing it. So this is kind of just, I meant to talk about it here, but someone mentioned it earlier. So there's nothing there we haven't already discussed. All right, so any questions about any of this stuff? Alrighty, so let's get to the most fun part, all the properties. So some of these we've certainly talked about, some of them else that we haven't, but probably make sense. So these are the 8 main properties of our vectors in Rn. So what's that first one? Which property do we call that? We actually showed that one geometrically already. Yeah, so addition is commutative. I have a question. Is subtraction commutative? We always talk about addition being commutative. Is subtraction commutative? It's a pretty weak theorem if the answer is kind of. Wow. Everyone's jumping on the yes bandwagon. Okay. So v minus u is equal to u minus v. Subtraction is commutative? Well, no. All right. No, subtraction is not commutative. All right. Anyway, back to reality. Associative. Yeah, our things are associative. What's number 3? What property is that? I mean, hopefully most of these properties seem fairly obvious, but if we add the 0 vector, we briefly discussed the 0 vector, but we didn't actually use it yet. So that one just says that we have a 0 vector, which isn't particularly surprising, but that the 0 vector is u plus 0 equals u. Anyone know what we call this negative u thing? Know what we call that? Here's where I see who's taking discrete math. No, not how we compute it, but what do we actually call it? That's certainly true. I'm not saying it's not the opposite direction. Anyone know what we call the thing? Yeah. Yeah, it's the inverse. Inverse of what operation? Right, so we actually call that the additive inverse, or the inverse of addition. Yeah. So we call that thing the additive inverse, the thing you add together to get the zero vector. Of course, that just gives us the negative, but that is what we call it. 5 and 6 are both examples of what property? Right, the distributive, and a couple more properties that are fairly obvious, but the fact is that we kind of have all of these things. Now, again, as a complete aside, our vectors in Rn satisfy these things, but a lot of other objects satisfy these as well. Matrices, for example, satisfy a lot of these properties, if not all of these properties. And so if you actually take the next linear algebra course beyond this, you'll actually see why things that satisfy these properties have some nice applications to them and stuff that we can use. For this class, you just need to know that these properties are true in order to use them. And so let's see, I'll give you a second to prove that k times u plus v is equal to k times u plus k times v, where k is a constant and u and v are in R3. No, so we tend to use little letters when we're talking about numbers. We tend to use capital letters. Before, we tended to use capital letters when we were referring to matrices. So when we saw similar properties for matrices, we like to use the little letters for the numbers and the capital letters for the matrices. So we're just sticking with that for consistency here. But in the list of the properties, there was L as well, just because one of them had, for some reason I flipped from L to M for some reason in number 7, but the idea is still the same. The little letters were the numbers or scalars, and obviously if they had an arrow over top of them, we were talking about vectors. Let's see if you can show this property here is true, where u and v are in Rn. Scary 5-letter word that starts with P. Prove. Actually, this one's not scary, just looks a little ugly. So when we say something's in Rn, so whenever we're dealing with theory, whenever we're dealing with a proof, it's what things mean, not straight up calculations. So what does it mean to be in this Rn thing? Right, it has n dimensions. So what would u look like? So what would a vector u look like if it had n dimensions? Doing A, B, C up to n would only really work if you had R14. Yeah, I'll stick with u so it matches the vector, but we could write it as u1, u2, all the way up to un. We'll go with numbers there instead of letters in order to, because there's no reason why we'd have to stop at 26. So what about v? V is also an Rn, so what would v look like? it would look the same, same in idea. Not exactly the same, but same as an idea. So yeah, we could use v instead of u, and we could get this. And k is just some number. All right. So first things first is, okay, it says u and v are in this Rn, so we have to write out what that means. Right? If u is in Rn, it's a vector with n components. So u1 to un, for example. Same thing with v, and k is not a vector, it's a scalar, so we work with it in that way. All right, so we're trying to show this property is true. Very similar to matrices, just less difficult. So if we're trying to show these things are true, what do we do? We're trying to show a property is true. So what do we do? Yeah, we take a look at the left-hand side, take a look at the right-hand side, show they're equal to each other. Same thing we did with our properties of matrices back in good old chapter 1. So let's start with our left-hand side. So order of operations, what do we do first? Add them together. So if this is u and this is v, what is u plus v? So the first component would be u1 plus v1. The second component would be u2 plus v2. Third component would be u3 plus v3, all the way to the end, un plus vn. So this is how we add vectors together. We did a bunch of examples with actual numbers. This one, we don't actually have the numbers, but it doesn't change how we add. We still add the first, add the second, so on and so on, all the way down the line. So we've added them together. Order of operations, we did what was inside the bracket. Right, so any questions about adding u plus v? All right, so now that we've done the addition, what do we do next? Okay. Now we do the multiplication. We multiply by the scalar, which means we're multiplying by k. So algebraically speaking, what do we do to multiply by k? Yeah, we multiply each component by k. ku1 plus kv1, ku2 plus kv2, all the way to the end, kun plus kvn. This is how we multiply scalar multiples. So I have asked a lot of questions back in chapter 1 about how do we do these kind of proof things. And the answer is you do the exact same thing you would have done as if they were numbers. Every step is the same step we would have done as if they were numbers. They're just not numbers. But in terms of what we do, it's the exact same thing. All right, and that's as good as we can do with our left-hand side. Any questions about how we, computed our left-hand side? All right, so what do we do with our right, what are we trying to show this is equal to? Crap, I gave it away. Yeah, we want to show it's equal to the right-hand side, so we do the exact same thing with the right-hand side. Except now, order of operations, yeah, that would be the same. Order of addition doesn't matter for numbers. Scalar multiplication doesn't matter for numbers. We're just trying to show the same thing works for vectors. All right, order of operations. For our right-hand side, what do we do first? The addition or the multiplication? Right, we do the multiplication. So that's going to be ku1, ku2, all the way to kun. So we've lost it a bit off the top of the screen. But here's u, and we're just multiplying it by k, which multiplies every component by k. What's K times V? KV1, KV2, all the way to KVN. So we've done the multiplication, that order of operations, that's what we do first. And then what do we do to add them together? So add the first components together, KU1 plus KV1. Add the second components together, KU2 plus KV2. Add the third components together, add the fourth components together, all the way to adding the last components together. And what do we need to be true? Right. Take a look at our right side, take a look at our left side, and we see that no matter how simple looking or how ugly looking they are, all that matters is that they are the same simple or the same ugly. There we go. And we've shown property 5. And honestly, unlike matrices where things get a little bit more crazy, these things here with the vectors, the properties are a little bit more straightforward. Okay. So any questions about vectors, their properties, how to add them, subtract them, and so on? If you do, let me know. That's the end of 3.1. I'm not going to start a section in 4 minutes, so we'll call that for today. If you have any questions, I'll stick around. If not, have yourselves a good day.